and continue the proof of the Pyros argument. So, okay, a quick reminder. So we had for a configuration in the local for a configuration inside the local configuration space with the plus boundary condition. So we defined incorrect points. We actually defined a plus correct point that was a point x in ZD such that sigma y is always equals to +1 every time the distance of y to x is not greater than 1. So in particular at x it will be 1 also. So there is a similar definition for minus correct. So x in ZD such that sigma y equals -1 for x minus y not greater than 1. Okay, and there was the definition of incorrect point. And an incorrect point was a point that's not plus or minus correct. So we defined the boundary of a configuration as being the collection of all points in the ZD such that x is incorrect. For sigma. So this is a definition that depends on sigma. And then we defined the contours. So for a configuration, sigma is a pair C, sigma C, where this is the restriction. Okay. Here, this is the restriction. To C. And C is a maximally connected component of the boundary. Okay? We also defined the volume of a subset. This will be important today. The volume of a subset that is finite is the complement defined by the complement of the unique unbounded component of the complement of lambda. So what this definition does is that lambda can have holes, and when it have holes, then this definition just gives you something that doesn't have the holes, where the holes are filled. So, and we also define the interior. Similarly, the interior is just the volume minus lambda. Okay. So, a few more names. Usually we call C the support of gamma, and we denote it by SP gamma. Okay, so the volume of SP gamma I will usually write as only V gamma. Okay, I will call, just to simplify things. And what else? Well, there is another point that we talked about yesterday, that when you have a contour, so let's say you have something like this, and then you have two holes, okay, and then the incorrect points is the white region. This white region here. Then we said yesterday that something happens. I asked you to prove it. That the sign of the configuration at this region is constant outside the connected components of the inner boundary. So the inner boundary of this set, for instance, is this. We have here. So it is not true that the configuration is constant at the inner boundary, but it is indeed true that you can that when you restrict to the connected components of the inner boundary, so in this case you have three, of them, then at each one of these components the configuration will be constant. So in this case I can also introduce something, a definition regarding this finite geometry thing that only makes sense in the case of the contour, and is the following. Well, I can divide the interior. Of the support gamma, that I will also write E gamma. I can divide it into two disconnected sets that I will call the plus and the minus interior. And what says that they are plus or minus is when you look at the sign of the outer boundary here of the hole. If you look at the sign and this +1, then this is the plus interior, and if this sign is -1, this will be the minus interior. Of course, the interior is just the union of these two cubes. Okay? So I needed to talk about this, and now what we are trying to do is to find the geometrical a nice geometrical substitute for that toy model with the boxes that we spoke about yesterday. We talked about yesterday. So now we need to see how this behaves with respect to the energy of the Hamiltonian. So before that, I want to go back to that discussion of compatibility, where we were talking about how if I have a family of contours associated to a configuration, so for each configuration I can break the incorrect points into, I can break its boundary into maximally connected components, and this will give me a collection, a family of contours. And then we said that this collection of contours may not be compatible if I erase one of the contours, simply because of the problem that since the contours mark the regions where you have incorrect points, so you can only have a change of sign inside this region. So if I erase a contour, I may cause some problems because, for instance, if this is +1, the inner boundary here, if I erase this, I will create incorrect points near here, and this will change the whole family of contours. So we need a way to erase a contour from a family, and somehow letting everything that is remaining after this operation stays compatible. So for this, I want to introduce to you the map tau. This is a map here, okay, that will depend on a contour. Is a contour, okay. And more, we'll ask that for this contour, we will ask that sigma x is +1 for some x in the inner boundary of the volume, okay? This is what we call a plus contour, actually. Call this a plus contour. So the inner boundary of the volume, remember the volume is when you erase these two holes here. So then the inner boundary is only the T-shaped green region. So in the case that this has a sign +1, then this will be called a plus contour. Plus contour. And this map that I will define works by erasing a plus contour, and it does the following. So for a given configuration, what you give you is, it will give you a +1 with x in the support of the contour. So this is what I mean by erasing, because then you eliminate this region of changing signs, and then you put it matching with the outside +1. You get sigma x, so it fixes the configuration. If x is outside the volume, or it is in the plus interior, so it does nothing when you are inside here or outside. So in particular, this operation will preserve any other contour that is outside V gamma, any other contour that may be present for sigma, and also the contours that are inside the plus interior. And then you take minus sigma x, so you flip the configuration, if x is in the minus interior. Okay? So what this last operation do is the following. Every point, you can see that every point that is plus correct becomes a point that is minus correct, and vice versa. But the incorrect points will stay incorrect, because if sigma x is different from sigma y, if I just take minus both sides, then they will stay different. So this preserves at least the geometry. It will, if there is another contour inside the minus interior, this operation will preserve the geometry of the sub contour. The contours that are there will have the same support, but now the configurations will be flipped. Okay. And then what we did for the toy model was to compare the energy between the existence of the box of -1 and the ground state configuration, that's everything equals to plus 1. So now we will go a step further, and we will calculate what is the energetic cost of erasing a contour. So what happens if what we will show is that we will calculate the energy difference between a configuration sigma and tau gamma sigma for gamma A plus contour for sigma. Okay. So what is the cost of erasing A plus contour from the family, from this family? So okay. So this difference is just this. So sigma minus h tau gamma sigma. We will calculate this. It's quite a lengthy computation, okay? So this is for you, Gilberto. So okay. First thing is that I want to simplify some things, and then I will call tau gamma sigma just tau, okay? And then we start the calculation. So what is this difference? This difference is the sum of all the local terms, jxy, tau x, tau y, minus sigma x, sigma y, plus the sum, and this is the boundary condition term, okay? So jxy tau x minus sigma x. We have a plus boundary condition, so it's just this term right here. So what happens is the following. If I denote by omega the family, remember, oh sorry, it's not omega, gamma, gamma sigma, the family of contours associated with gamma, I will write V gamma when I mean the union of the volume of each one of its contours. Okay? So what is nice about this set is that the incorrect points for sigma will always be inside V gamma. Okay? So if this happens, this means that outside V gamma, okay, outside V gamma, in the complement of V gamma, you only have correct points. But remember, this set V gamma doesn't have holes. So if it doesn't have holes, the complement is just the unbounded component. Actually, it's just the definition, okay? It will be exactly the unbounded component. And since the boundary condition is plus 1, this means that the sign of the spin will be plus 1 for every x outside V gamma. Okay? So we will use this input to calculate this thing over here. So let us first look at this thing over here. So this will be x and y psi lambda jxy tau x tau y minus sigma x sigma y. Okay, so the orange part is this, but then I can divide lambda into the set V gamma. Okay, the case where the 2 points are inside lambda minus V gamma. Plus the case where I have 1 inside V gamma, 1 point inside V gamma, and another point in lambda minus V gamma C, the complement. Tau x tau y minus sigma x sigma y. Okay? Well, what I do know by our previous discussion is that outside V gamma, I will always have the signs to be equal to 1. Okay, so this will be 1. And by the definition of the mappa tau, outside V gamma, I just maintain the same configuration. So since we are outside V big gamma, right? So this will also be 1. And this gives me that this term over here is 0. This is the first thing. And the other thing is the following. So by a similar reasoning, if y is over here, then I know that tau y is equals to sigma y, and then sigma y is equals to plus 1. So this will be plus 1, and this will be plus 1. But look at the boundary term right here. I can divide this boundary term as being a sum over x inside v gamma, y inside the complement of lambda, jx y, tau x minus sigma x, plus this. Lambda minus v gamma, y outside lambda c. Yeah, outside lambda. So by the same reasoning, in this region the sign of the configuration is constant and equals to +1. So this is +1, this is +1. So this whole thing is actually 0. And what happens is that if I sum this quantity over here, that is exactly equal to this one. It's not equal, but it's similar to this one. Okay. Then I can write the difference between energies as being the sum of xy inside v gamma, jxy, tau x, tau y, minus sigma x, sigma y, plus a boundary condition term, x inside v gamma, y outside v gamma, jxy, tau x minus sigma x. So the first thing that I can see that follows from this this calculation is that the size of the box disappeared in this difference. What remains is only the information that is happening of what is happening inside V gamma. So what is important for the difference of energies is just what is happening inside this finite set. Okay. But again, we can further divide this sum into smaller sets, okay? Because what we have is that we are erasing just gamma. So there are many more subsets where I have equality. So again, let us take a look at this term. And then I will divide it into the sum of xy inside V gamma minus V gamma, the small one, tau x, tau y, minus sigma x, sigma y. Okay? Plus the same thing, but now inside V gamma, plus the interaction term between the two sets. So V gamma minus V gamma y inside V gamma. Tau x, sigma, tau x, tau y, minus sigma x, sigma y. So again, what is happening in this case? Well, first is that outside V gamma, again, the sign is fixed by the tau transformation. So this term right here will be equal to 0 because tau x is equal to sigma x in this region right here. I have here the same thing. I don't know what to do with this term yet. And for this last one, what I do have is that I have that tau x here will be equal to sigma x. Okay. Well, I didn't like how things turned out, so I just change here. The system is usually symmetric by this change of variable. So y will be here, x is here. So this is sigma y, sigma x, and this is, oh sorry, this will be sigma x, and this will be tau y. No, the other way. So tau x, because x is inside V gamma, and sigma y here. So, okay, I erased another term, but what is happening to the boundary condition term? This one. So for this term right here, it's usually easier. So you have the sum x inside V gamma tau x minus sigma x jx tau x minus sigma x V gamma minus V gamma and y outside V gamma. So, okay. So again, this term I don't know what happens, but this one I know happens. Outside V gamma, the configuration is just sigma x, so this will also be 0. So joining every term that is not 0, so these two terms with this one, I get that the difference of the energies will be the sum over what happens inside V gamma, jxy tau x tau y minus sigma x sigma y. I still don't know what happens inside here. Plus, I will sum these two quantities right here, remembering that outside V gamma the configuration is always +1. So if I write a sigma y here, I know that this sigma y is just +1. So there is no problem with the signs. And then now this term, this spin-dependent term, is the same as this one. And then summing these two regions, I get V inside V gamma, y outside V gamma, jxy, sigma y, tau x minus sigma x. So this is another interesting thing, that when I erase specifically one plus contour from the configuration, the difference between the energies is something that only depends on the volume of the contour that I erased. Any questions, Gilberto? Do you have? Okay. You can ask in português if you want, okay? Você pode perguntar em português se você quiser. Tá bem? Okay. So, what's the next step? So, in V-gamma, there are different regions, and there are different regions behaving different according to the sign of the configuration. So I will further decompose this component as its support union with its interior, okay? And then what I get for this quantity here is, again, the sum of xy inside the support, tau x, tau y, minus sigma x, sigma y, plus what is happening inside the interior, plus a term that is interacting between both regions. The interior of gamma. But remember, what this map does is the following. When x is inside the plus interior, this will give you just sigma x, and when x is inside the minus interior, then this will be minus sigma x. So this means that when the 2 points are inside the same region, the same part of the interior, then although I may flip the sign of the configuration, I will flip both of them. So this implies that this quantity over here, the spin part, will be the same value. So this means that this quantity over here will be equal to the sum over x inside the minus interior, y inside the plus interior. This is the only region where I have both signs changing. And then for x inside the minus region, I will have minus sigma. And for y inside this region, I will have just sigma y. And then this means that this is just minus 2 sigma x, sigma y, jxy. And this is this term will stay as it is. So, okay, another thing that happens, another interesting thing that happens, that for this term right here, both x and y are inside the support. So if both of them are inside the support, then tau x and tau y is just plus 1. So this means that this quantity right here is just 1 minus sigma x, sigma y. And then I can write it as a characteristic function, 2 times the characteristic of sigma x different from sigma y. This will also be important. And then what happens to this term right here will depend in what part of the interior y is. And this I can divide into 2. This I will write the following way: x inside the support of gamma, y inside the plus interior jxy, and then here I know that this will be x is inside the support, so just 1, and here we'll have sigma y minus sigma x sigma y plus x in the support, y in the minus interior, and then I will have jxy minus sigma y minus sigma x sigma y. Okay, we are almost done. So first, for these two terms right here, notice that I can write sigma x sigma y minus sigma x sigma y. If I just sum 1 here, I sum and subtract 1, then I get that this term will also be equal to this one, so this will be 2 times sigma x different from sigma y, and this one right here I can write as minus 2 times the characteristic of the set of sigma y being equal to minus 1. So what this is just 1 minus sigma y over 2, and then I have a minus 2 times this, and then I get what I want. So similarly, I can write for this term minus sigma x sigma y. I can write by the same trick. Then I get minus 2 times sigma y, but now the sign changed. So this will be sigma y equals to plus 1 plus 2 times sigma x different from sigma y. Okay? Then I will plug this over here. This means that this sum will have 4 terms. Okay? This term will have 4 terms. We'll have the sum over x in the support, y in the plus interior, jxy times 2, because there is a 2 over here and a 2 over here, of sigma x different from sigma y. But see, I have a term that depends on sigma x different from sigma y in these 2 terms, y in the minus interior and y in the plus interior, so I can write this just as the sum of y inside the interior of the contour, and then minus the remaining terms. So this will be jxy, x inside the support, y in the minus interior, and then I will have sigma I equals to plus 1 minus 2 times jxy, sigma y equals to minus 1, x in the support, y in the interior, in the positive interior. Okay? And then right now I cannot do anything more with these terms right here. Okay, so there is one remaining term before we finish this calculation, and the remaining term depends on the boundary term. So this will be this term over here. This term over here. And what I get when I do this is the following. So this will be the sum of jxy, x inside the support, y outside the gamma, and then I will have sigma I tau x minus sigma x plus jxy, x inside the interior, y outside the gamma, sigma y minus sigma x, sigma y. Oh, sigma y here, tau x minus sigma x. Okay, so again, what happens here? Here I will have 1 because x is inside the support. So this whole quantity right here will be actually equal to sigma y minus sigma x, sigma y. And I already know that this decomposition holds. So then I can write the orange part as 2 times the sum over x inside the support of gamma, y the complement of gamma. So here I have jxy, this characteristic, plus minus actually 2 times sigma y is equal to minus 1 x inside the support, y outside the gamma. So this is what I get for this term. And then I'm already finishing. I have to analyze what happens to this case. So this case I will have again two cases depending on what part of in what component of the interior you are. So if you are in the plus interior, so if y is in the plus interior, then this term will be so. Okay, let me do with care so you can follow. So for this term over here, so I divide it into 2 terms, jxy sigma I, and now since I am in the plus interior, for instance, this will be sigma x, sigma y, sigma x minus, oh wait, okay, so since I am in the plus interior, then tau x equals to sigma x, and then this will give me 0. So this is 0, okay? This whole term is 0. So the only part that is important here is the part with the minus interior. minus interior y b gamma c jxy. And now in this case the signs are equal, so here I will have minus sigma x, so then I will have minus 2 sigma x sigma y over here. So this quantity will be equal to this minus 2 sum of x inside in minus gamma jxy sigma x sigma y inside y outside the gamma. Okay, so now I completely eliminated tau from the problem, but I got many terms, so now I will collect every single one of them. So the first term that I will sum is the following. So therefore this will be equal to, so the first thing that I want to do is the following. This term will be 2 times the characteristic of sigma x different from sigma y for this set, for an unordered pair, inside the support. And then I will change it, okay? And then I will change it by a sum. I will change it by this sum. Y inside the support. We already did this trick before, but when I do this, the cost is that I need to erase the 2 because I'm doubling the sum, okay? I'm counting pairs twice. This is the thing. So, okay, if I get this term right here, with this modification, and with this thing over here, and if I get one of these terms, so I took one support and one interior, so this will be a sum depending on x is inside the support and y in the volume of gamma. And then I sum with this term right here, only one of them, then I will get the sum for every x in the support and y in ZD, jxy, sigma x different from sigma y, plus, now there are 2 terms here. I already summed one of them, then there is still one depending on the volume outside the volume of gamma, outside the volume of gamma. And here I also have something depending on the interior, since I summed only one of them. But now I don't have another term of the support. So I just have interior and the outside of the volume. This is just the complement of the support. So this will be, there is a term that depends here. Sigma x different from sigma y. X inside the support, y outside the support. Okay, these 2 terms, now depending only on the support. And now for the terms depending on the interior, what I have is so I have what are the terms remaining? So this one I already took care of, so this one also. and also this one. Okay, so the remaining terms are this with the interior, depending on V gamma C, okay, this term right here. So there is also this term right here that is similar to this one, sigma x, sigma y. Then I will have minus 2 x inside the minus interior, y inside the union. So the union of the plus interior with V gamma C, sigma x, sigma y. V gamma C, okay, so this one, okay, this one was okay, and this one. So what are the terms remaining is these two terms. I have these two terms remaining. And this term over here. Yeah, exactly. So x in the support. So plus the remaining terms. Okay, I'll just write everyone here so we can see them. So this will be the sum from x inside the support, gamma, y outside V gamma C, okay, jxy sigma y equals to minus 1, minus 2 times the sum of jxy, x again on the support, y inside the interior, sigma y equals to plus 1, minus 2 times jxy. So okay, sigma y equals to minus 1, x inside the support, y inside the plus interior. So this is the exact form for the difference of Hamiltonian. So notice that this is an exact computation. So this holds whenever whatever jxy is. So for instance, we are interested in phase transition not only for the nearest neighbor Ising model, but also for the long range Ising model. And this calculation also holds for the long range Ising model. So when we arrive in the long range case, we will start from this formula, okay? So now suppose that we are in the nearest neighbor case. So for the nearest neighbor Ising model, what is the nearest neighbor Ising model? Jxy equals to j if x minus y is 1, where j is a positive real number, okay, and 0 otherwise. So what happened in this case? Well, remember that the inner boundary of the contour, when I draw this picture for the contour, the inner boundaries, the interiors, were these sets, these green sets over here. And I told you I asked you to do this exercise, that the sign in the inner boundary of the support is constant, okay? So what happens if this is the plus interior, okay? So if this is the plus interior and this is the minus interior, what happens is that right outside the boundary of the interior, this will have a -1 sign. And here I have a +1 sign, right outside this set. So so this means that in order to leave this set and arrive at this set, I will have to have a plus configuration and then have some change at some point until I reach to the minus configuration. So this means that the plus interior and the minus interior will always be at a distance larger than 2. They will always be at a distance larger than 2. So this means that this term right here will be 0, okay? And again, by a similar reasoning, since the contour is a plus contour, if I am in the minus interior until I reach the outside the volume, since it is a plus boundary condition contour, then I will have to change the sign. So the distance is also larger than 2, so this term is 0. Okay. This term here is sigma I equals -1 outside V gamma. But what happens is outside V gamma, what I have is other contours, okay? And again, in order to reach them, I have to have a changing sign. So the distance between the support and any other of the contour is also larger than 2. So this quantity will be 0. Here, the support and the interior, they don't have distance larger than 2. But see, I am only summing points here where the sign of the spin is equal to +1. But since this is the minus interior, and right here I will have also the minus sign, okay? Because this is a change of regime. So here I will have to have minus correct points. So this means that the distance from the support to the points inside the minus interior, such that the sign of the spin is +1, is larger than 2. So this will also be 0. And by a similar reasoning, this will also be 0. So every single one of the terms in the second line are 0. And then I get that the difference between the energies is just depending on the support of the contour. So jxy sigma x different from sigma y plus jxy x inside gamma, y outside the support, where sigma x is different from sigma y. So this is also exact. So just to remember the toy model, the difference between the ground state and the energy of a box was related to the boundary of the box. So this is something similar that is happening, because if I consider the case of the boxes of the toy model, you can see that since this is all minus and outside is all plus, then the support of that contours were only the inner boundary of, or almost equal to the inner boundary of the cubes. Okay, so so this somehow generalizes what was happening to the case of the cubes. So okay, and now this is where I can get with equalities. The problem now is that usually it may be very hard to calculate this quantity. Okay, so what we will do is the following: we will give a lower bound to it. So since this term, the difference of energies, will appear, this is somewhat foreshadowing of what will happen. Since this term will appear in the Gibbs weight, this term will appear as exponential of minus beta. So in order to give an upper bound, I need to give a lower bound to this quantity, and then what I do get is that first this quantity is larger than 0. Okay, so I don't have to care about this quantity here, and this one will give me the following. This quantity here is the sum for x inside the support of gamma, the sum of y inside zd, jxy, sigma x different from sigma y. But remember, we are in the ferromagnetic, the nearest neighbor case, so this will be j only when x is a nearest neighbor of the point of y. So x minus y equals to 1. Sum this characteristic function. So what is happening now is the following. Since in the support, for a point to be in the support, some of at least one of its neighbors will need to have a change of sign. So this quantity right here will always be larger than 1. So this will be larger than j times the support of gamma, that I will denote j gamma. So what this means? Although we are erasing a contour, to understand the phenomena that's happening, it's better to think backwards. So in order to, if you have a configuration, that have some contours and want to create a given contour, then what this quantity is saying is that your system, in order to create that contour, will have to have more energy, and the energy cost to create this contour will be at least J times gamma, the support of the gamma. So this means that in order to create very large contours, I will need to have very large a very large difference of energy. So, okay. So let us go back to the pyros, going back to pyros argument. I guess I didn't say this the last class, but the strategy of writing this as something that is geometric and show that the magnetization will be positive. The argument is known as Pyros argument. Pyros was the first one that thought about this. He was, I guess, in 1904, if we thought about this. But then it was ignored for during a part of the last century, and then when Onsager solved the pressure and saw that there was a phase transition for the Ising model, then people started to take a look again at the Pyros argument, and then in the 60s they gave a rigorous version of this argument. So everything that we are going to do, the idea was from Pyros. So now the quantity that we want to see is this one. Sigma 0 equals -1. Okay. And we want to show that this is less than 1/3 uniformly on the box. This is our strategy that we talked about yesterday. So notice that if sigma 0 is -1, what is happening is that, and I have a plus boundary condition, this means that the sign will have to change at some point, okay? The sign will have to change at some point. So there are two possibilities for this set, for sigma 0, for the site 0 here. And the possibilities are sigma 0 is inside the support of some contour, so the point is incorrect, or sigma 0 is inside, it's a minus correct point. So if it is a minus incorrect point, it must be inside the volume of some contour. So this means that this probability is upper bounded by the probability of existing a contour inside the family gamma sigma, okay, such that so and why this is an upper bound, why this is an upper bound, because if 0 is inside V gamma, it can be a plus correct point, for instance, and I guess it's better to give a drawing. For instance, this is an upper bound because of this. I can have the following situation. So 0 is plus, and then I have plus everywhere. Okay, so 0 is a plus contour. Okay, oh, plus contour, no, sorry, it's a plus correct point. But then I have a shell of minus points here, and then I have plus everywhere. So what will happen is that the incorrect points, all these points are incorrect, but this point is plus correct. So this will be actually the plus interior, and this weird shaped losango will be the contour. So this is a case where the contour have a sign plus on 0, so the volume contains 0, but it's not here. A configuration that satisfies here is not a configuration in this event. Okay. So yeah, and also another thing that I can ask is the following. Since I'm just asking that 0 is inside the volume of a contour, I'm not worried about the fact that there are many other contours inside this one. I just need it to be inside some contour. So so this means that in order to have an upper bound, I can have another restriction here, and the restriction is that gamma is external. And I will explain this. External means that there is no other gamma prime inside this family such that V gamma is strictly contained in V gamma prime. Okay? And what is nice about external contours is that I can guarantee that the sign at their boundary will always be plus, because outside I have a plus boundary condition. So these are always plus contours. The external contours are always plus contours. So, okay, I can, what I will do next is to make a union bound is that I can make a union bound by a sum over all the contours such that 0 is inside V gamma of this probability. So this exists a contour, so I just can take a union over all the contours. And then here I have the realization of a specific contour. So so here is the event of all sigma such that gamma is inside gamma sigma. This you can check that is indeed a measurable event, because since a contour have both the information, then to have a contour to a configuration sigma have gamma as one of its configurations, you just need to check the configuration inside gamma, and then you know if sigma has gamma as one of its contours or not. So okay. Now we proceed to bound this quantity right here. So this, I know exactly what this is. This is the sum over all sigma over all configurations, okay, such that gamma is inside gamma sigma of the weight exponential minus beta plus sigma divided by the partition function. Okay. Then I will make the following trick. I will write exponential of minus beta I will erase this. So exponential of minus beta h, the configuration tau, exponential of beta h plus the configuration tau. Okay? So then, by picking these two terms right here, then I have exponential of minus beta, the difference that we just analyzed, exponential of minus beta h tau. Okay? Oh, no, okay. So, since I have this lower bound, and I have a minus beta here, this will be an upper bound. This will give me an upper bound. Beta j gamma. But now this doesn't depend on the configuration, so it goes outside. So this will be this probability will be less than exponential of minus beta j times the support times the sum over all the configurations, such that gamma is one of its configurations of exponential minus beta h tau plus divided by the partition function. So we are almost done now. I will make another trick right here. So I will write this sum. I will split this sum over here in layers in the following way. I will sum over all possible tau on the configuration space. Okay, let's say overall omega. Okay, and then I sum overall all the configurations omega. Okay, such that gamma is inside gamma sigma, and the tau transformation of omega will give me of sigma will give me exactly omega, and then exponential of minus tau. But this quantity right here is constant because it's the map tau is applied to it. So this will be just exponential of minus beta h. This will go over here plus, and then omega. And then here I will have just the sum of ones, and then I will have to count every sigma such that gamma is in gamma sigma and tau omega equals sigma. And you can notice that for many configurations omega, this quantity will be actually zero because the set will be empty. Okay, because for instance, if omega is a configuration that has different contours from sigma, it can be very different. Then since the map tau fixes the configuration outside the volume of gamma, if the configuration omega doesn't match with the configuration sigma, then the set is empty. Okay, so what are the degrees of freedom of this set? How many points we have here? So okay, suppose that now we have fixed what is happening outside the gamma for configuration omega, and it happens to be equal to sigma. So what else can change? So since inside the interior of gamma I have a fixed sign, I have sigma x if it is the plus interior. This means that I'm also fixing the spins of omega inside the interior. Similarly for the minus interior. The only degree of freedom that I have is what is happening inside the support, because every time that I pick a sigma here and I go to the support, then and I go to the support, I erase everything and put just a +1. So this means that this set can only vary inside the support of gamma. Any possible configuration inside the support of gamma. So this will be less, since we have only 2 spins. This will be less than 2 times gamma sum over all the configurations, exponential minus beta h omega plus. But we are dividing by the partition function, okay? Beta plus, and this is exactly the partition function. So this is 1. And what we get is, finally, we get that this probability over here, beta plus 0 equals -1, will be less than a sum, a series of all the contours, summing over all the contours, such that 0 is inside the gamma, of exponential of minus of log 2 minus beta j, the size of gamma. So this is nice, because notice that now I don't have any information on the finite volume lambda. So this bound is finally this bound is uniform in lambda. So what I just need to check is that this sum if this sum is convergent or not. So how do I do this? I will divide again, and I will split the sum into level sets. So I will sum all n larger than 1. Okay. Oh, sorry. Okay, this is 0 inside here. And then I will sum over all the contours such that 0 is inside the gamma, and that the support has size exactly n. Exponential of log 2 minus beta j over n. Oh, sorry, this size, but this function is constant on this set, so this will be the sum of this series over here. So log 2 minus beta j n times what? Times the number of contours such that 0 is inside V gamma and its size is exactly equals to n. Remember, for the toy model, when we reached this point right here, we had something like the translates of the cube with side r. And this was a very, you have very few translates of a given cube that contains 0. But now, if you remember the construction, you are essentially counting how many connected subsets of ZD have size exactly n. Okay? And if we can show that this set right here of all the contours such that 0 is inside V gamma, and gamma equals to n. If this is less than the exponential of some constant, so if we can show that there exists a constant, a positive constant, that can depend only on the dimension of the set of ZD, okay? A positive constant. Then, if I plug this information here, what I would get is the following. If I can show that something like this happens, so this series would be exponential of log 2 minus beta j plus c times n. But beta is a degree of freedom that I have. So if I take beta large enough, so for instance, if I take beta, so I want log 2 plus c minus beta j to be less than beta j over 2, for instance, okay? So what this minus beta j over 2, so what this imposes to me is that beta would need to be larger than log 2 plus c over times 2 over j, right? So if beta is larger than this quantity right here, this means that this series will be less than a geometric series exponential of beta 2 and a geometric series, and this I know what is this is exactly exponential of minus beta j over 2, 1 minus exponential of minus beta j over 2, and then if I take beta, I can make this quantity as small as I want when I take beta large. So since this quantity bounds the probability of seeing a spin minus 1 at site 0, this means that at some point of the beta, for the parameter beta is a real number on the positive real line. So at some point, this quantity will be less than 1/3 that I told you yesterday. It would suffice, and then the phase transition is proved for this case. So it all depends on this calculation over here. How many connected components of ZD do I have? So we will start proving this theorem tomorrow, and then we will start to discuss the results from Rodrigo's paper on communications of mathematical physics on phase transition for the nearest neighbor case when you add a decaying field. So see you tomorrow.